Here's the missing video. We often have to deal with high dimensional data. We've worked with patterns that have 3 inputs, 2 inputs, 4 inputs. But as you're well aware, large networks will work with hundreds, thousands, possibly of inputs at a time. And dealing with such high dimensional data poses problems of its own. When the domain from which the data is drawn that a network works on are from the domain of images or sound in particular, which are very beloved of deep learning networks, then the dimensionality goes through the roof. So if we have, let's say we're trying to present what we think of as an image to the network, we can represent the image using numbers. Let's say we've got 500,000 numbers representing an image of a puppy dog on the carpet. Now, remember, the network only ever gets the numbers. It doesn't know anything about puppy dogs. If we have 500,000 inputs, then our specific data point, our input pattern, is a single point in a 500,000 dimensional space. You can't really visualize a 500,000 dimensional space. 2 dimensions, 3 dimensions, they're fine. 4 is hard. 500,000 is out of the question. Mathematicians are well used to this. They often develop insights in spaces of 1, 2, 3 dimensions and then generalize to arbitrarily large dimensional spaces. Now, the auto-associator that we saw in Unit 6.1 gave one way of reducing the dimensionality of a set of patterns. So we're squeezing patterns which are quite large at the input layer through a bottleneck at the hidden layer which has less units. So that the numbers, the 500,000 numbers at the input, now are reduced to maybe 5 numbers at the hidden layer. So that's one way of reducing the dimensionality. The problem is so general that it occurs well outside of neural network field, and the standard approach here uses something called principal components analysis, which is a very important technique, quite simple to understand, and it's a way of teasing out or finding what's really significant in a set of high-dimensional vectors. Take, for example, this data set here on the screen. You can see it's a two-dimensional data set. So we're going to hone our intuitions using something rather smaller than 500,000 dimensions. This two-dimensional data set exhibits some variation. And as it's plotted there, you can see that it's not entirely homogeneously distributed. Rather, these points lie more or less along a line with some variation on either side of it. Principal components analysis is a way of re-representing these without changing the data or changing them only in very principled ways. Primarily by re-rotating the axes. So you can imagine the x and the y-axis, not shown on this plot. Y-axis vertical, x-axis horizontal. Now if we rotate that axis scheme, we're changing the numbers by which we describe the data points, but we're not changing the relations among the data points at all. And that's the insight from principal components analysis. What we'll do is take our x and y axes that meet at the origin, and we plonk that origin down in the middle of the data set. And then we'll rotate the axes so it'll look something like this. I've moved the 0 point to the middle of the data, and then I've rotated it so that the x-axis now rotates to the position shown by PCA1, or principal components axis 1. And the y-axis now is PCA2. Why would we do this? Well, what we can then do is choose to selectively look at just the first or the second component. That is, to look at a small number of the dimensions that characterize the data. So in this particular case, whereas previously there was equal variation among our data points when you consider them horizontally or vertically, By rotating the axes, now most of the variation lies along the first principal component and much less of it lies along the second principal component. So if we were to then only look at the first principal component, we would still see an awful lot of the distribution of our data. We'd lose some information, but we would retain as much as is possible to retain with a single dimension. So here's how it works. First thing is to center the data. That means take the 0 point used to establish the center of the center of reference of our coordinate system and move it into the middle of the data. Have people then, if you've got a number of dimensions, you may choose to scale the data so that they have a mean of 0 and a standard deviation of 1. That is known as converting to standard scores. If you've done any statistics, you've met that. That's an optional intrusion, messing with the data. The important thing is we move the origin to the middle of the data, and then we rotate the coordinate axes so that the first axis, say the x-axis, captures as much variation as possible. Having fixed the x-axis, if we have many more dimensions, we then rotate the remaining dimensions around the x-axis until the second axis captures as much variation as possible. Then we fix that and carry on with the remainders. So if we have 2 dimensions, as we just saw, when we fix the first axis, the second axis is also fixed. If we had 3 dimensions, having fixed the first axis, we could then still rotate the other 2 to capture as much variation as possible along one of them. And there'll always be the last one is fixed. So principal components analysis doesn't actually reduce the dimension of the data. What it does is it ensures that our description of the data is constructed in such a way that looking at only a few of the dimensions, that is like looking at a shadow instead of a 3-dimensional volume, looking at some of them will be as maximally informative as possible. So it's a principled way of choosing to reduce the number of dimensions that we consider. And in a way that's very similar to what our auto-associator is doing, because it's also reducing the dimensionality of the data. But the auto-associator, remember, is a non-linear transformation. Each unit in the hidden layer computes its net sum and then passes it through this S-shaped function. Principal components analysis never bends these axes. There's no non-linearities involved. So one way of thinking about what an auto-associator is doing is something like what principal components analysis is doing, but allowing more bends in the construction of the axes. You don't have to think of it that way. Principal components analysis, by virtue of being a linear technique, is clean, simple, quick, very easy to do on standard statistical programs. And is one way that you might choose to analyze hidden unit representations. So if you have 7 hidden units and you want to understand those patterns, we've seen hierarchical tree clustering. That's one way of looking at them. Another way of looking is to take that 7-dimensional data set and just look at the first 2 principal components. Now, describing this in words is not necessarily the best. The best thing to do is to play with this. And there's a URL for a demo on the web that you can actually go and get a feel for the technique yourself, to play with it a little bit. And I encourage you to do that. It's a widely used technique, standard tool in the box. Then we're going to come to a related technique, and this is rather an oddball neural network. This is work that was done in the 60s and 70s when neural network research, as we've seen, was absolutely not popular. Tuomo Kohonen was working in Finland, and he was ploughing his own furrow, looking at his own way of linking simple computational units and seeing what you can do with them, inspired by different aspects of brains, perhaps. He came up with a technique to develop a network called a self-organizing map. This is also a dimension-reducing technique. It is non-linear. And what it does is it takes data from high dimensions and collapses them down to 2 dimensions so that we can see things. 2 dimensions is great. We can see in 2 dimensions. It's a very powerful generic technique. has found widespread application, is still popular today. There are instances of cortical connections that are known that closely resemble, it appears, what Kohonen networks do. So let's just have a look at this. Here you can see the network, and what's shown here is the two-dimensional output grid. That's our principal focus here. There is an input layer for which, imagine we have n input units. Let's say n is 500,000 or 50 or 5. It doesn't really matter. We present one vector at a time down there. So the bottom of this figure is the input. And these input patterns all project up to all the two-dimensional grid of output units. So we're mapping here from an n-dimensional vector to a two-dimensional grid. And we may have thousands of n-dimensional vectors. And what we're interested in is how the similarity relations that obtain among those high-dimensional vectors, how they appear when we collapse them all onto this two-dimensional grid. So we could collapse onto a one-dimensional grid. There are examples of this. But usually it's two dimensions precisely because we can visualize things better that way. The goal here is that patterns which are close to each other in the high-dimensional space should, where possible, map to spatially adjacent or close points in the two-dimensional output grid. The input patterns are connected to the output grid using weights, which are just like our normal weights and also just randomly initialized originally. And there's a training method to set the weights in order to bring some coherence to this mapping. And we initially use small random numbers as usual. And the algorithm looks like this. You start off with random weights, and then you're going to go through a loop until the change in weights stabilizes. So the algorithm is such that large changes will occur at the start of the process, and the size of the weight changes will get smaller as we go along. So for each input pattern, we present the pattern at the input, and then we allow the grid of output units, each of them, to calculate their values. Now, there's no particular coherence to this at the start of the process. But one unit will, by chance, have a maximal activation when we compare all the units of the output. So we find that unit and we say, aha, I see you saw this pattern. Okay. Now we're going to consider you and your neighbors, those units which are close to you, and we're going to update the weights so that the next time this pattern occurs, you and your neighbors are going to be selectively more sensitive to this. And we repeat for all the patterns, and we do this many thousands of times. We start off with a rather large neighborhood, and we reduce the neighborhood over time. So it starts off like this. If this is the two-dimensional output grid, imagine the yellow dot there is the winning unit. We change all the weights that lie within the circle just a little bit, so that the next time this pattern is presented, they're all selectively more sensitive to it. And as we go through the network, through the training patterns again and again, we gradually shrink that network size. And in this way, the response properties, the sensitivities of the units in the output layer, become tuned to the similarity relationships that obtain in the input set. Once more, my words are probably not the best way to learn this. So there is a demo a lovely demo which gives you multiple examples of this. It's on the web and you can play with this there, and I encourage you to play with it. And what you're seeing here is yet another dimension reduction technique, this time usually to 2 dimensions. And what you're seeing is that the projection from the input space to this 2-dimensional grid begins as a chaotic mapping with no order or coherence to it. And the training algorithm has the effect of bringing a coherence to the sensitivities of the output layer, so that patterns close together in the training set in the high dimensional spaces appear or map to points which are close together in the output layer. So go play with those 2 demos if you want to get a feel for both of these. Here you go.